So, hi everybody. I'll quickly do an introduction and kickstart this panel. First of all, welcome to this panel on everything about ZK and validity rollups. There's a little bit of contention on what it should be called, but we'll dig deeper into that in just a bit. But anyways, we have the best speakers to come and talk to us about this topic. We are going to be doing a technical deep dive on the technology. We have Ellie from Starknet, co-founder of Starknet, Brendan, who is the co-founder of Polygon Zero, and Alex, who is the co-founder of Matter Labs, which builds ZKSync. I don't think the people on this panel need any more intro, so I think we should get into the motion as soon as possible. Before that, just a quick word on how we're going to be structuring this panel. Rohit and I are going to be co-hosting it, so we're going to be going around and asking questions to the panelists that we've already prepared. This would go on for about 40 minutes, and towards the end, we would be happy to take a couple of questions from the audience as well. So please keep them handy. That's about it. Let's get started. I'll hand it over to Rohit. Maybe Rohit, you can start off with the first question to our panelist.
Thanks, Madhavan. Hey guys, great to meet you. Eli, nice to see you here again. So maybe I want to ask Alex first. So I think it's really hard for people to grasp what is ZK rollups / validity rollups. So maybe you can tell about what are ZK rollups / validity rollups by bringing some differences or explaining some differences between optimistic and the ZK rollup side.
Absolutely happy to answer this. And I actually thought of some interesting metaphor. So with both rollups types, optimistic and ZK, what we actually using is the technology of containerization. So you can think of it as, the early containers that emerged in the 1950s on the ships. Before the shipping containers were introduced, it took 100 people around 7 days to unload a ship. So actually, people would physically go, take the sacks of some stuff and move them out, and it would take very long because you need to go many times. When containers were introduced, this time was reduced from 100 people 7 days to 7 people in 1 day, because you could use cranes and you could transport the same amount of stuff just a lot more efficiently. And if you want even deeper intuition where this efficiency is coming from, just think you're going to a grocery, you're buying a bunch of products, and then you need to go and bring them to your home from the car. If you have to carry every single one, you're going to waste a lot of energy, a lot of time just like doing these repetitive moves. Whereas if you pack everything in one backpack, then you can do it in one move. And even though the backpack is slightly heavier than each individual, or like actually a lot heavier, right? But you just do it once, so your overhead is still minimal. So containers are at the core of rollups because different resources on blockchains have different pricing. They have different bottlenecks. They have different profile of pricing. So we have computation, we have storage, we have data bandwidth, and all of them are slightly different for the full nodes that operate a blockchain, that verify every single transaction on the blockchain. And by full nodes, I mean actually like light client, something like full Ethereum client, not the validator nodes. Those are separate. So the full nodes of individual people have different profiles. So in Ethereum, the Ethereum's goal is, and similar for Bitcoin, is to make the job of running a full node very easy, so that we can have as many of those nodes as possible. So we keep the blockchain truly decentralized and resilient. We have tens of thousands of people running them on their consumer laptops. So you want the bandwidth to be low, you want the storage requirements to remain under what is reasonable to store on a single laptop. And you want computation also not to exceed, not to heat up the CPUs of this processor, right? So we can, the job of rollups is to make sure that we can process large blocks on those hardware nodes much cheaper by packing them together. So, but the zero knowledge rollups are like, I think, yeah,
Hey, no, no, no. I was just applauding to the fact that's a great analogy. Please go on.
Yeah, so we can go and describe the difference between optimistic and ZK rollups, like exactly, like which is like optimistic rollups use fraud proofs, ZK rollups use validity proofs. ZK rollups verify every transaction beforehand, right? We use proofs of computational integrity to produce a succinct proof that we have processed a very large number of transactions. Optimistic rollups rely on watchers who like when a sequencer presents the result of the computation, it is up to anyone to challenge this result and then play an interactive game theoretical process on blockchain to actually prove to the parent system, to layer one, to Ethereum, that this was wrong. But coming back to my analogy, like if you think of rollups as containerization mechanisms, so ZK rollups or optimistic rollups are something like sailing ships loaded with containers. You can still put more data through, but you have other factors that you don't really control. Speed of wind, the direction of wind. You have to navigate it in the right way to get from point A to point B. It depends on some factors, how secure, how sure you will arrive. Whereas ZK rollups are something like nuclear powered ships loaded with containers, where you can use them in a rollup mode, just carrying over containers much more efficiently, much more reliably, because you just depend on the laws of physics. You don't which you control, like on pure engineering, on some mathematical calculations you made beforehand. You checked your system, and now it's secure. Like it will surely get you there, no matter what weather it is. But it can be also used separately. You can, like, if you detach it from the containers from the ship, you can use it to build railway or hyperloops or something like this, where you use this atomic energy, which is very powerful, which essentially scales infinitely, because we have a lot of nuclear fuel material to use on Earth. So we it's not like fossil fuels. It's not like renewable energy, which is still in very early stages. We have a lot of that. It will be enough to go around for everyone. But you don't use containers. Like you can power electric cars, for example, which everyone owns their own sort of container, their own vehicle to transport things. But you get this energy which is infinitely scalable. So like ZK rollups are interesting in this regard because you can use them in Validium mode, where you use this infinite scalability for computation, but everyone will have their own storage, data availability, storage and data availability, managed on their own, but still having the full security that transactions are not messed with by validators, that no funds can be stolen, no state can go corrupt, and so on. So sorry for a long answer, but I thought this will be a comprehensive one.
Hey, I love that answer. This is the first time I'm kind of hearing that analogy. Alex, is it kind of fair to say that optimistic rollups are based on game theory and ZK rollups, validity rollups are based more on math? Can you just double click on that point that you made a little while
That's
earlier?
absolutely correct. That's absolutely correct. So maybe we can let other panelists expand on this. Maybe we
Sure.
start with Eli, and I just want to add to say a word of congratulations to Eli and the entire Starknet team, who just raised a big round.
Thank you.
Oh,
Thanks.
yes, absolutely. Congrats, Ali, and the entire Starknet team.
Yeah, thank you.
Maybe if I could put in Ellie on this follow-up question. Ellie, when I was like talking to you, coordinating for this conversation, you mentioned a very interesting point that hey, probably ZK rollups is not the right way to address this technology, but validity rollups is something better. Can we use this opportunity to pick your brain on why you feel so, and also give us an understanding of what ZK
hmm
rollups are not, or what is this technology not?
Okay. The rollups called ZK rollups, they have one very small problem, which is that mathematically speaking, they do not employ ZK proofs. Zero knowledge is a mathematical and cryptographic term that has a very specific meaning. So the reason I quibble about this is like, you could say there's this amazing car. It's a really great car. It's very efficient. It's an electric car. But then what if, and you're describing a car that is, let's say, a Prius or even just some other car that's very efficient, but not an electric car. So, you don't want to call it an electric car. And then the term ZK rollups hints that people are using something called ZK proofs in them. Well, they're not. All of the rollups that are called ZK rollups do not use ZK proofs. For instance, Starknet is not a ZK proof, and to the best of my knowledge, I think the plonks used in ZKSync are also not necessarily zero knowledge, and so on and so forth. So that's my quibble with it. Now, I just want to explain a little bit how it works and the difference with optimistic rollup. It's all of these rollups, and if you think about it, blockchains, are all of them basically just innovations on integrity. And integrity was beautifully defined by C.S. Lewis as meaning doing the right thing even when no one is watching. And in the context of computation, you can specify a program that defines what is the right thing to do with data. For instance, you transfer funds from one account to the other only if the owner of the first account consented, let's say via a digital signature. So a program should check whether there's a digital signature on a payment, and if so, you can sort of change the amount in that account and move it to wherever the sender wants. Okay, so we would like the world to operate with integrity, but we would like our banks to operate with integrity. And the question is, how is integrity achieved? So in the conventional world, it's achieved by some manual process in which auditors and accountants look into various computers and reports and make sure that everything's okay. And if something is not okay, then you can call the police and file a complaint and things like that. That's the conventional world. Bitcoin and following it all, blockchains made a huge innovation in offering a different way to reach integrity. Basically, integrity in numbers, in big numbers. Everyone is invited to check the integrity of every transaction. And this is a beautiful, democratic, inclusive, it's an amazing principle of transparency and so on. And that's why we love blockchains. However, it is inefficient because now we all need to run these computers that check everything. So that's why we have a bottleneck in scale. Okay, so optimistic rollups say we will incentivize economically a protocol in which anyone who wants can be an accountant and an auditor and run some big computer and check some other computers. And if you trust an optimistic rollup, you're putting trust in this game theoretic incentives, right? That the remuneration is correct and the auditors won't cheat you, and that they're incentivized not to cheat, and so on and so forth. In a validity rollup, you're putting your trust in math, because the way a validity rollup works is that every time there's an update to the state of the system, the integrity of this update is supported with a proof. And the proof proves integrity. And mathematically speaking and cryptographically speaking, it is impossible to generate a proof for anything that was not the right computation. So that's basically what a validity rollup gives you. And now, if you have a validity rollup, you could have a single prover that you don't need to trust, process a very large number of transactions, and then submit an update to the state of the system along with a succinct proof that is easily verifiable. And then all the blockchain needs to do is verify this proof. And, for instance, our systems, the Starknet systems, have been settling transactions, say, for DYDX, upwards of $600 billion have been settled over the last year or so. And the integrity of all of these settlements is basically guaranteed by the Stark proofs that are attached to these updates.
Thanks for that explanation, Eli. And just wanted to ask this specifically once again so that it is clear to everyone's mind. So when you say that Validium rollups does not use ZK proofs, most people, when they think about ZK, they think about zero knowledge, and they understand ZK from very analogical perspective, which is you are trying to prove a statement without telling what the statement is. You are basically proving that a statement is true without telling what is the exact statement. So are you saying we cannot even use that analogy in case of Validium rollups, or you are just mathematically speaking that ZK proofs are specific to the term itself?
Well, what I mean is, first of all, what mathematically speaking, what a ZK proof guarantees is something a little bit different than what you stated. So there is a statement, and it is essential that everyone see the statement. So now the statement may or may not reveal some information, but it is what is proved, and everyone sees it. Okay. You say that a proof is zero knowledge if when you watch the proof, right? The proof is sometimes a protocol, there's some questions and answers, and then you go back and ask yourself, did I learn anything additional from watching this proof? So if the answer is mathematically speaking, no, you provably have not learned anything from watching this process. And even more mathematically, what it means is you could have, whatever information you think you got from watching this process, you could have gained by yourself by playing some game with yourself. So if the proof can be proven to reveal no information beyond the integrity of the statement, then one can say it's a zero knowledge proof. Now, as a matter of fact, the Starks used in Starknet or StarkX are not zero knowledge. They do leak information. The Plonks used in ZKSync, to best of my knowledge, but Alex incorrectly, do leak information, and so on and so forth. So the actual proof systems that are deployed on Validity Rollups just are not ZK proofs. So, I don't want to call a system that is not, I don't want to call a very nice car that is not an electric car. I don't want to call it an electric car, even if I like it a lot. So by the same token, I do not want to call, systems that do not deploy ZK proofs. I don't want to call them ZK, ZK systems. And it also leads you down a direction of asking about privacy and whether it gives you privacy. And again, the fact of the matter is that Starknet and ZKSync are not promising any privacy right now. They're about scalability, but everything there is completely transparent. So, I just think that the sort of a historical mistake calling these things ZK rollups. They're just not.
Thanks a lot for that explanation, Eli. And this is the first time I've been able to get that into my mind. So also wanted to ask Brandon, since Polygon has been working on various kind of validity rollups, I'll let Brandon clarify if they use any kind of ZK in their rollup. What are the differences in the different kind of validity rollups or ZK rollups Polygon is working on? And maybe give some insights on what are the basic tech differences, and we keep hearing these terms like Starks, Snarks. So what is all these very high on my mind technology or terms are all about?
Yeah, sure. So I guess to your first question, they would technically be validity rollups because we don't use blinding in our proofs. So they don't, as Ellie said, they don't satisfy the ZK property. I think for Polygon, we can broadly distinguish between rollups that are EVM compatible and rollups that are EVM equivalent. And so if you want to build a rollup, you need that can support arbitrary contracts. We're effectively building a VM whose operations can be verified with a zero knowledge proof. And so we have two options in doing that. We can either build a VM that's efficient inside the snark, whose operations can be efficiently verified or represented in an arithmetic circuit, or we can build a zero-knowledge proof that that efficiently verifies EVM bytecode. So something that actually takes EVM bytecode and is able to verify that the execution of some program was actually valid. And so so at Polygon, we sort of have the luxury of being able to pursue both an EVM compatible rollup, which is MIGAN, and also I think this is really exciting, an EVM equivalent rollup. So we have Polygon Hermes and Polygon Zero that are pursuing this approach of being able to actually take existing Solidity or EVM programs and verify that their execution is correct. And so there are trade-offs on kind of either side of this category. So EVM compatible rollups are a little bit faster, but they also require compiling from Solidity or from Yule into a different bytecode representation, whereas EVM equivalent rollups allow us to use existing tooling and sort of have a closer user and dev experience to the Ethereum L1. And so I guess for your second or your third question, within Polygon, all of our ZK teams are extremely collaborative, and so we're all converging on using very similar primitives. So we use Starks to actually verify the like VM execution for transaction proofs, simply because air-based Starks are more efficient to verify that, I guess, format of computation. And so we all use the Goldilocks field, which we pioneered. That's extremely efficient. We all use recursion in slightly different ways, and we all focus on using pairing-based proofs to wrap our final Stark proofs, so that we can reduce gas consumption on Ethereum. So does that sort of get to your question? Sorry, it's kind of a rambling answer. I didn't come prepared with a very elaborate analogy, so apologies.
Sure, if I may double click on that, Brendan, maybe for the interest of the audience, what is the differences between a Stark and a Snark? Maybe at a high level. Maybe Alex, you could also chime in, because I know ZKSync is based on Snarks, if I'm not wrong.
Yeah. So a Stark is uses a different arithmetization, and so if we think about an arithmetic circuit, we can think about how gates are wired to one another. And so if you think about something like Planck, we can express an arbitrary computation, and any gate or any sort of like step in the trace of this computation can access any other gate in the circuit. Whereas with air-based Starks, it fundamentally is designed to verify a computation with repeated structure. So we have steps in the trace, and each step has access to the step immediately before and after. And so it just, I'm sure Ellie can talk about this with a little bit more eloquence, but it just refers to like how we write constraints and which computations are sort of efficient to represent.
Sure. LA, Alex, do you want to add on anything to the Stark versus Snark differentiation?
I can say a few words. So these are two mathematical or cryptographic definitions, and each one of them defines a class of protocols or proof systems. And really, one can focus on what the acronyms mean in each one of them. So I'll start with snark. So snark, the letter S means succinct, which often refers to a constant number of group elements as part of the proof. So it's already assuming often that you're working inside some group, and often this group is actually some elliptic curve group. Even though that's not essential, one could also define succinct as just being logarithmic in the amount of computation. And then N means non-interactive, which means that your proof is basically a string and you must have one string, and there's no interaction going on. However, in a snark, you're allowed to have, or actually you must have some setup process, and the setup is allowed to be even something that involves various secrets that cannot be revealed, known as trusted setup or toxic waste and things like that. So that's what a snark is. Now, and by the way, the keys generated can be as large as the computation needed to be proved. That's fine according to the definition of a snark. A Stark, the letter S there means scalable, which means that the proving time must be extremely efficient, nearly linear, and at the same time, the verification time cannot be more than logarithmic in the amount of computation. And the second letter is more interesting. Transparent means that all the verifier does is generate public random coins. In particular, there can be no secrets, no trusted setups, and also no long keys, proving keys or prior information. This is extremely useful for scaling, because you need ever larger and larger circuits, and with a Stark you don't need to have some ceremony for generating them each time anew. Other than that, Starks also allow interaction, whereas Snarks do not allow. Now, practically speaking, I think often Snarks are, in the practical usage, things like, Zcash and Plonks and other things that are usually referred to as Snarks. One thinks of something that uses a lot of elliptic curve cryptography and things that are prone to be broken by quantum computers. The proving time there is slightly larger than in Starks. However, they have the individual proof size is extremely small. It's under 1 kilobyte and sometimes even under 200 bytes. And Starks, they are post-quantum safe. They have very, very efficient proofers. However, the size of the proof is roughly 100 times larger. An individual proof is 100 times larger than an individual snark proof. So instead of 200 bytes or 1 kilobyte, they can be in the range of 20 to 100 kilobytes. So those are roughly the differences, but both have their use cases and they're deployed in many, many places. Snarks appear in, of course, Zcash was the first thing. And then you have them also in Filecoin and, Plonks and other areas. They appear in Mina, in Aztec, in ZKSync, other places. And Starks appear on Starknet and StarkX, and the Mir protocol and other teams inside the Polygon are also working on them. So they both have their uses and will be around for a while.
Perfect. Alex, I know you got cut off a little while earlier. Is there anything that you would want to add to what Brendan and Ali just mentioned?
Or maybe share a perspective on why ZKSync choose to build using Snarks. What advantages do you feel it gets you?
Sure. Yeah. So we are using Plonk, which is very similar in arithmetization to Starks. So arithmetization is the way to represent your program that you're trying to prove in mathematical form as a big polynomial or as a set of polynomials. And the primitives and the approach we're using there for Plonk is very similar. So eventually, I think that all projects will just pick the proof systems that are most efficient, most advanced, and it will be easy to switch between these proof systems because they are all converging. So the only big difference today between Starks and Snarks, like a really big one, is the footprint on Ethereum. When you verify a proof on Ethereum, Starks are roughly 10 times more expensive, but they are transparent. they do not require any trust whatsoever from anyone. Well, snarks are much cheaper to verify, 500, 600,000 gas, but they involve this trusted setup ceremony, which most people reuse existing trust, like the ceremonies with. We use the one called Ignite, organized by Aztec 2 years ago, where Vitalik Buterin participated. A lot of famous people participated, like something like 200 participants, and if at least one of them was honest, then it's safe. But that's roughly the biggest practical difference today. In the future, I think we will all move towards transparent proof systems, like fully transparent, and they will be cheap to verify, because either we will get something that some improvements in Stark generation or in Stark verification, or improvements in Ethereum itself that will make these transparent proofs much cheaper to verify. So eventually everyone will converge. It's not a big issue.
Got it. I think that's a great wrap up to this particular subsection on stars versus noise. Thank you for summarizing that really well, Alex, with the trade-offs. With that, Ellie, I want to bring you in on one of the points that Brendan was referring to a little while earlier, that is around EVM compatibility. And I know that Starknet is not EVM compatible. And can you explain what aspects of the virtual machine architecture like make it suboptimal to run validity rollups? Like what is the reasoning behind choosing an architecture that is distinct from EVM?
Yeah. I mean, I'll just give by analogy. You know, when Ethereum started, there were a large number of programming languages out there that are really great, you know, Python, C, Go, whatever. So one could ask, why in the early days of Ethereum did people construct, you know, a new model, the EVM, a new programming languages, you know, Yule, Viper, Solidity, and so on? Why? It's not because, you know, Vitalik and others were not aware of the existence of amazing programming languages, right? There was something different, and the something different is that you have a new set of constraints that you suddenly have to deal with. So it just doesn't work as well with existing programming language that were built for something else. Now, enter proof systems. They are defined very naturally over weird settings, you know, finite fields, the complexity parameters there, what makes something efficient or not efficient. These parameters are very different than what you have both in Solidity and also in existing programming languages. Okay, so now what happened was for us, you know, we started initially by writing basically constraint systems, the analog of like circuits by hand. And this took us to a certain place, right? We could do some things, but then at some point we figured out that it's just impossible for us, for humans, to sort of define more elaborate computations using, you know, just placing polynomials on some ephemeral board. Okay, so what do you do? The solution we decided to go with was we developed internally a very simple CPU architecture that has like, you know, program counter and like 2 registers, that's all. And a very simple memory model, read once, continuous, and a bunch of other things that are very simple, but at the same time powerful enough to allow you to express a lot of computations. And then we started internally to write all kinds of systems in this new framework. And it worked extremely well for us. You know, all of the StarkX systems are written in this programming language, which is called Cairo. So we figured that it's good enough for us internally, and you can get much, much, much more scale if you write in this language. So since the thing we want to deliver is the maximal amount of scaling via a validity proof, we found ourselves using a programming language that is not as elaborate and as standard as something like Ethereum or Python or Go or anything else. But it was extremely useful in reaching the one thing we wanted, which was to create scale. And then we said, well, if it's working so well for us, why not, expose it to the world? And so we said, let's Starknet use that. Now there is a transpiler from Solidity to Cairo, and there will be more and more, tools that will take you from various programming languages into Cairo. So at some point, maybe you can use just plain Solidity or C or something like that, and press a button and everything will run efficiently. But the fact of the matter is that today, there are dozens of teams that are developing on Starknet, and even though they would have preferred to write in Python or C, they also share our vision and our realization that to reach scale through a validity rollup, your best bet is to learn a new programming language, and write code in it. That's basically how we ended where we are.
So I agree with you, Alai, and like we have been writing Cairo for the last 7 months or 8 months, I guess, and I agree with the experience. So wanted to hear a little bit from Brandon as well, since Polygon Zero is EVM compatible. Like, what are the challenges did you face when, like, or what are the biggest challenges you are trying to solve when you are approaching it from an EVM compatibility perspective?
Yeah, great question. So, so I think before we joined Polygon, when we were Mir, we had a very similar experience and perspective to the one that Eli has, where we're really focused on optimizing for proving time efficiency, and we sort of viewed that as the main constraint. And I remember before we joined Polygon, we were thinking about sort of the approach that Hermes is taking, the EVM equivalent approach. And we just thought, it's impossible that this could ever be efficient, that we could ever generate proofs in a reasonable amount of time, because the EVM uses primitives that are really expensive to verify in an arithmetic circuit. So things like Ketcheck and ECDSA. So we profiled Ethereum transactions and found out that the average Ethereum transaction uses Ketcheck like 13 times. And we were estimating the proving time to verify a single invocation of Ketcheck at like 1 to 2 minutes, optimistically. And what's interesting is in the last 6 months, our view and our perspective has completely flipped, because we've been able to make so many improvements and advances in our underlying proving systems that actually we no longer view the main constraint as prover efficiency. We view it as like the thing that we want to optimize for is the developer and the user experience. And because we're trying to attract Ethereum developers and sort of piggyback on this really well-developed ecosystem around Ethereum tooling, we actually view EVM equivalence as the optimal path forward. And so to give an example, like I said, we thought that Ketcheck would take 1 to 2 minutes to generate a proof for a single invocation. So if you extrapolate that to proving a transaction, it would take us like 15 minutes to prove that a single Ethereum transaction is valid. But with the proving system improvements that we've made, we're now proving 100 Ketcheck invocations per second on my MacBook Air. And so like we've seen this wild improvement in proving time and prover efficiency. And that sort of led us to focus on EVM equivalence and delivering a really good experience for developers and for users of Ethereum. And so, I think that there are still challenges and areas of inefficiency. I think Ketcheck is one. I think 256-bit arithmetic in the EVM is one, ECDSA, but we've actually managed to address all of these, and we're really confident that we're going to have a rollup that's low latency, low cost, and high throughput while maintaining EVM equivalence. So that's sort of our perspective and where we're headed.
Got it. Thanks for shedding light on that, Brendan. With that, I want to pull in Alex. Alex, when we visit your website, it says in bold letters, trust math, not validators. So can you help us understand, like, what are these validators and what are the other moving parts in a validity rollup or ZK rollup? I know there's like validator, prover, sequencer. These are like terms that I keep hearing about. What are the most important moving parts in the stack of a rollup?
Sure. So let's start with validators, which is easiest. It's something all the systems have, rollups or not rollups. Those are people who validate transactions. So it's a network of nodes that check, verify the validity of the transactions. You don't need them in a ZK rollup. You rely on the validators of your base network, which is Ethereum. You just rely on all the full nodes of Ethereum. So they are your validators. Now, and in Ethereum, you don't really rely on them. You don't trust them as well, because any honest minority can always fork away. So with Bitcoin, Ethereum, you don't trust them. Those are trusted systems. The next role which you have in any rollup would be a sequencer. It can be centralized, it can be decentralized, it can be permissionless, where anyone can act as a sequencer in a certain moment of time. Let's define sequencer as a block producer. It's someone who gets the transactions together, rolls them up in a block, and then submits this block along with some things, some proofs, and some other things on layer one. And then for zero knowledge rollups, and yeah, Eli had a point that they should not be called ZK rollups, it should be called validity rollups, which is technically correct. But Vitalik came up with a nice correction, which keeps things historical, and we can just say ZK stands for zipped by cryptography, and then everything works. So with ZK rollups, you need also provers, people who will, or nodes or actors who will generate the proofs for your block, which you're going to submit to layer one, because you will need to submit also the proof.
Got it. So you mentioned about the sequencer as well as the validator, but I think we've also been talking a lot about the prover. What role does the prover have to play?
Well, the prover generates the proofs, right? So it can be the same entity that also runs the sequencer. It can be a decentralized marketplace for proofs, a distributed protocol to generate the proofs, crowd source the proofs, and so on. So you can this is a separate role, but it can be taken on by the same entity. Does this make sense? So you're just as a sequencer, it can be a single server that accepts transactions from the users and then rolls them together in the block, or it can be some consensus protocol that is run by multiple nodes that all get transactions from the users in a decentralized manner through a peer-to-peer network, and then they decide in a way of consensus on what is going to be the next block, and then they elect someone who will submit this block on Ethereum.
Got it. Yep, that makes a lot of sense. Thank you. Hey, Rohit, you want to go? I know you have a question.
Yeah. So just wanted to ask Brendan, like, so you also use Stark proofs. So in that case, like, is it different compared to like what Starkware uses? And like, why do you choose those kind of differences? Like, can you first go about, like, are there any differences when you use Stark proofs compared to Starkware?
Yeah, sure. Good question. So we in the past we've really obnoxiously said that we're no longer living in a Snark versus Stark world. We're living in a Plonky 2 world, and that's like a totally obnoxious thing to say, but we, it's just tongue in cheek. But I think it gets to this point that we have fully transparent post-quantum safe snarks that use Fry as a polynomial commitment scheme, which is the same thing used in Starks. And so we are able to take advantage of a few things there. The first is that we're able to use really small fields that are particularly efficient on modern CPUs, on modern GPUs and FPGAs. And the second is that we're able to take advantage of this really important trade-off that's present in Fry and in Starks. And so with Fry, there's this trade-off between proving time and proof size. And so on the one hand, we can have really, really fast proofs that are really big. So they'd be way too big to efficiently verify on Ethereum without consuming way too much gas. And on the other hand, we can have slow proofs that are more size optimized, so we can actually verify them on Ethereum. And so that creates this sort of difficult trade-off for Starks, which is we need to make our proofs fast enough to generate in a reasonable time, but also small enough to be verified on Ethereum without being way too expensive to fit in a block. And so one of the things that we've done that I think has been a big leap forward for the industry is we've made recursive Fry and recursive proofs that verify Starks really efficient. So we no longer are bound by this trade-off because we can have, like for our expensive proofs, for us that's verifying Ethereum transactions, we can have really, really fast proofs. And the proof size is big, but it actually doesn't matter because we're aggregating those proofs recursively. And so they're never actually being verified on Ethereum. They're being verified as part of a recursive proof that's been shrunk and wrapped in a pairing-based proof. And so if you think about like Starkware, and this is nothing against Starkware, like they're amazing researchers, and this work is only possible because of the work that they've done. But they have to pick between this trade-off where a batch has to be fast enough to be generated in a reasonable amount of time, while also being small enough to be verified in Ethereum. And we are no longer bound by that trade-off. And so that's a big part of the reason why we can generate proofs extremely efficiently, because we can take advantage of Fry in a fast configuration to generate the expensive proofs, and then wrap them and aggregate. So we're not paying an exorbitant gas cost on Ethereum.
Great. Thanks for that explanation. So I wanted to touch a little bit on the decentralized aspect on validity rollups as well. Maybe Eli, you can share, like, so as far as I understand, none of the validity rollups are decentralized today. So what aspect of validity rollups architecture are we referring to, and when we talk about decentralization? And can you explain like what part of it is actually decentralized, or maybe let's call it, name it trustless instead of just calling them decentralized, and what parts are maybe require some form of trust or maybe not decentralized?
Okay, that's a terrific question. So, okay, the proof systems and the math behind them mean that when you go with a validity rollup, even when it's not decentralized, it's pretty safe. Let me explain what I mean. So suppose there's just one entity running the whole system, and now I'm referring to a rollup. Soon we'll touch also on Validium, which has a different trade-off. So let's take, for instance, DYDX is such a system. It's a full rollup, but it is operated only by basically the DYDX and Starkware. So let's put them together as a single team. So even if DYDX and Starkware are completely malicious and want to wreak the most havoc that they want, so they cannot steal funds, right? So in the DYDX system, there's roughly $1 billion of USDC locked. Even if we wanted very much to take those $1 billion and move them somewhere, this is not possible because there's a verifier on chain that is needed. There's a smart contract that every change to the state of the system must be accompanied by a start proof, and we don't know how to. It is mathematically intractable to generate a proof of something that didn't transpire. Okay, now what we could do if we were to turn malicious would be to shut down the service, meaning we would stop to service everything. In a rollup system, it's a big inconvenience, but you could start retrieving funds from the L1 system directly. Okay, so it will of course be very, very inconvenient for a while to the users of, let's say, the DYDX system. But they would get their funds eventually by just talking to the L1 smart contract through something called an escape hatch. So just to summarize this, even before decentralization, if you're working in a rollup mode with a single operator, if you have an escape hatch mechanism, then the worst thing that could happen is that for a period of time, your funds would be locked and it would take you some time and some process to take them out. But funds cannot be stolen. Now, in a Validium system, before decentralization again, what happens is that the full state of the system is not, does not appear on layer 1 Ethereum. So now there's more danger. And what is this danger? So there's a committee, a data availability committee, that need to sign that they have the data before the system could be advanced. So what could happen is that if all of these entities turn malicious, so all of the data availability committee members, along with the operator, let's say Starkware in the case of Immutable or Sorare, so on, were to turn evil, again, funds cannot be stolen, but now the data availability committee, along with the operator, could ransom the system and say, look, it's stuck in a state that we're not telling you about, and pay up or do something so that before we release it, which of course would be very unfortunate. So that's why you want decentralization, both for the L1 and for the L2. So what would decentralization mean, let's say in Starknet? It would mean that there are two and maybe three new entities. One is a sequencer, which is the analog of the miner or block producer, right? This is an entity, and now it's decentralized, so there's some way to pick for each block a sequencer. And the sequencer will basically put a sequence of valid transactions. There's also a role for a decentralized prover, which is the entity that will take either one block or several blocks and produce a proof that is submitted to layer 1 of the validity of all transactions there. And then a third entity that is not needed in a rollup case, but in a Validium or a ZK Porter or Volition or things like that, you would want it, is a decentralized data availability committee. So if you want to move from rollup to Validium and have things decentralized and safe, there's room for this third class of entities. So decentralization, just to sum up, would give you decentralized sequencers, decentralized provers, and maybe decentralized data availability nodes. And all of these are to prevent basically freezing the system and leaving it stuck in a state that no one can advance. But theft of funds, direct theft of funds, is prevented by the start proofs.
Wow, that is quite an elaborate answer. Thank you so much, Eli, on that. Alex, do you want to add anything to what Eli just mentioned as well? And just for the audience, after this, we'll take one question from the audience. I don't think we'll have time for more than that. Alex.
Yeah, I would love to add to this. Eli has explained that validity proofs itself prevent. You don't have to trust your sequencer, your rollup of validators, operators, whatever you call them, but for the integrity, for honesty. However, there is one aspect where you still have to trust them, and that is, or like two aspects. One is liveness, and one is censorship resistance inside layer 2. So yes, you can rely on escape hatch on layer 1 to enforce transactions on layer 2 and to bring your funds out through a sequence of complex calls. And we can design different. The devil is in the details there. Like, do you need to think about it as a contract developer, or is it by default? Like, all contracts enjoy the same properties. Do you as a user have to produce your knowledge proofs to use the escape hatch? Like, how expensive is that? If you have to spend $1,000 but you only have $50 in the rollup, then you're not protected, really, right? So like, there are a lot of questions which we cannot cover now, but they are very important. But regardless of the escape hatch discussion, we also want to guarantee that you will have censorship resistance inside layer 2. This is very important because otherwise you can have a system that is controlled by very powerful actors and that will only allow certain types of transactions, maybe most transactions, most types, most classes of transactions, just not yours because they don't like you personally, or because you belong to a certain minority, or because you have, like certain powerful players just want to exercise their power and silence you because you're a political dissident, or what, like you can come up with a lot of different cases. So for this, it's crucial if we want to remain in the trustless spirit of blockchains like Ethereum, like Bitcoin, like this true maximalism in the best sense of this word, we have to preserve decentralization also at the sequential level. And that includes the technology to decentralize, like some consensus mechanism or maybe different approaches, or something what I really like how Arbitrum is solving this problem, where they allow anyone to be a sequencer, anyone can produce a block. But also, like, even if you have a consensus, you need to make sure that the system is broadly decentralized, and you need to come up with ways to decentralize it so that it doesn't end up being controlled again by a small group of people with a lot of capital who will then dictate the rules there. So I'll just leave it for you to think about.
Thanks, Alex. I think I have one last question, which is about, is there any possibility of, since like all of you are working on different kind of proofs, is there a possibility of, let's say, snark proofs getting accepted on Stark? Maybe Ella, you can answer that, or maybe like that's not even a relevant question. Can you like give a light on that?
Yes, it's a terrific question, and not only is this possible, it's actually already being done. So people, so people have written code for verifying. Wait, I'm not sure if. No, I'm taking that back. I'm not sure if people have published Cairo code for verifying a pairing, so maybe that's not quite. But people have posted code for verifying a whole bunch of other cryptography, like I think Schnorr signatures over different curves and things like that. And it's very much doable. I think actually it will actually be done. Yeah. But I'm not sure it's already. I don't think someone wrote it already, but it's not that hard to write it, and it will be done. So people will be verifying snarks and starks. And then
That awesome. Thank you so much. I think we are now running out of time. This was like super enlightening. Maybe with that, I would like to thank all the panelists for joining in and giving so many insights. I might have to re-listen to this multiple times to digest all of it. But maybe before we sign off, if you have any advice for developers in this audience, especially in the bear market, maybe you could use that as a final remark.
I'll start. I'll say, look beyond the markets and build something that you believe will exist once you go back, once the bear market ends. And do your own research, explore all of these roll-ups, optimistic, validity roll-ups, and make your choice wisely. Because the most important resource that we have is the time we spend on various things.
Alex, you can go next.
Sure, I just want to add that the systems that we represent here on this panel have been built in bear markets. So don't get discouraged by the cycle movements of the financial markets. You just build stuff, focus on the fundamentals, be frugal with your resources, with their costs, and just get a team of people who really believe in what you're building. Think what's going to be the next problem after the current problems are solved, and it's the best time to build because you don't have a lot of noise. You don't have this FOMO of I should have launched some scam project. You can only work on something that makes sense, and you have a lot of people who are doing the same, who will encourage you, and you will build good networks, which are also very, very important if you want to promote to make what you're building successful.
Awesome. Thank you. Brendan, last comment before we drop off.
Sure. Yeah, I just to echo what Alex and Ali said, I think the bear markets are great for building, and my advice would be to focus on the newly possible, so things that were not practical or possible to build on Ethereum. So whether that's taking advantage of higher throughput on rollups or building things and building ZK applications that are now possible with more efficient primitives. I'm really excited to see what comes out of the next few years. So.
Thanks a
Awesome.
lot, guys.
Awesome.
It has been pretty amazing to have all of you here. And if any of you are curious to build on anything, reach out to any of us, me, Madhwan, Eli, Alex, or Brandon. And I'm sure all of us would like to help each other and build together.
Thank you, Madhav, and thank you, Rohit.
Thank you, folks. Thank you so much. This was amazing. See you then. Bye.
Thanks, everyone.
Thanks. Bye.
Thank you, guys.